Okay, so last day we were looking at kinetics in an attempt to sort of elucidate organic reaction mechanisms, and there were a couple interesting points that we learned last day. One was something called the method of initial rates. Right, the method of initial rates. And in that method, what we did is we would mix known concentrations of your reagents, and we would measure the relative rate of the reaction. But we would do so within the first 5 to 10% of the reaction. And the idea was that at the beginning of the reaction, we will show that we have the largest rate, and therefore, since the number that we're measuring is large, then small errors are sort of absorbed, and we tend to get very minimal overall errors in the process. And the other reason was that at the beginning of the reaction, there is also minimal product interference, so that it is to your advantage to measure the reaction rate at the start of the reaction, so within the first 5 to 10%. And that is the significance of the subscript 0. The subscript 0 is what identifies this as a method of initial rates. We said that normally when we're doing this reaction in practice, or these experiments in practice, what we would do is we would vary the concentration of one reagent and keep the other one constant. This is typical scientific methodology. You vary one variable at a time and study the other. We also said that essentially what happens in a reaction, for example, if I say I had, let's say 2A plus B, and that's the example we had last time, gave rise to C, and I had 1, 1, 1, let's say I had 2, 1, 2, and I didn't record the one we had in class, but let's say it was then 1, 2, 2, let's say. What I would do next is say, well, look, I'm going to use my first line of data as the reference, because that's when the relative rate is 1. And then I'm going to ask, what have I done to the concentration of A? And the answer is I multiplied it by 2. And that means that the rate of the reaction is going to change by a factor of 2 to the power of little a. Where does that little a come from? It comes from one of the other important things we learned last time, which is the rate equation. And the rate equation for a reaction of this type involving two reagents will be written as rate is equal to K, which is the rate constant, times the concentration of reagent A raised to the order of the reaction with respect to A, times the concentration of B raised to the order of the reaction with respect to B. So that little a and little b are the orders of the reaction with respect to reagent A and reagent B. And I would say that the overall order of the reaction would then be equal to the sum of A and B. The important thing with the rate equation is that the rate equation identifies which species and how many of them are involved in the reaction up to and including the rate determining step. So this tells me that AAs plus BBs are involved in the reaction, in other words, the steps of the mechanism, up to and including the rate determining step. Okay? And that is the value of the rate equation, because it gives us a window as to when species are involved in the reaction and how many of them are involved in the reaction. It's important to notice that where's my mouse? Here we go. That little a is not necessarily equal to 2, and little b is not necessarily equal to 1. In other words, the orders of the reaction are not necessarily the coefficients in the stoichiometric equation. So if I go back to this then, and let's see how this is used, is that if I look at it, as I multiply the concentration of A by 2, I must multiply the reaction rate by a factor of 2 to the power of A. In other words, whatever I do to the concentration of a given reagent, I will do to the reaction rate raised to the order of the reaction with respect to that reagent. So obviously I've kept conc of B constant, so I'm not changing that. So I can deduce from this then that 2 to the A, right, that 2 to, I can deduce from this that 2 to the A is equal to 2, right? 2 to the A is equal to 2 because I multiplied this by, I multiplied 1 by 2 to the A, which in essence means multiplying 1 by 2. So 2 to the A is equal to 2, which means 2 to the 1. And I can infer from this that A is equal to 1. In other words, the reaction is first order in A, right? And of course you notice that this 1 is not 2, right? Because the coefficient in the stoichiometric equation does not dictate the value of the order. Although, as we said in class last day, it does dictate the maximum order. So this reaction can either be 0 order in A, first order in A, or second order in A. Similarly, it can either be 0 order in B or first order in B, because the value of the coefficient here is 1. And 1 therefore is the maximal value of the order. We are not, in this course, going to look at fractional orders, right? That's something you will need if you're a chemistry major or a chemical engineer. You'll need that in Chem 390, Chem 391. Okay, so if I were to continue this for reagent B, as I keep conc of A constant from lines 1 to 3, again, I double the concentration of B, and it turns out the rate also doubles. So I can infer from that that 2 to the B is also equal to 2 to the 1, and therefore B is equal to 1. So my reaction then would have been first order in both A and B. So what that tells me then is that 1A and 1B are involved in the reaction up to and including the RDS. 1A and 1B are involved in the reaction up to and including the RDS. So if I ask you to draw a mechanism for the reaction, you can tell me, well, maybe in step 1, A plus B react to give some intermediate W, and then W reacts with A to give C. I will define step 1 as the RDS. Now, by the way, given the kinetics, I know the reaction must be multi-stepped, because I have 2 A's to be in the stoichiometry, and yet only one of them is involved up to and including the RDS, which means the other one, comes into reaction after the RDS. So the reaction must at least have 2 steps. Again, when I sum the steps of these 2 reactions, right, these 2 steps, the W gets crossed out, and overall I have 2 A's plus B give rise to C, which is the stoichiometry I observed. I can then draw a reaction profile diagram, and let's say I told you that for the reaction 2A plus B, this in fact was an endotherm. Well, it's an endotherm. Well then, if I were to draw the reaction profile diagram, sum of H against reaction coordinate. I know overall it's 2 steps, that's the one I chose, and overall it's an endotherm. And I know step 1 is the RDS of my mechanism. So I draw a profile that looks like this. And here I'll have 2 A's plus B. Here I will have C. Now if you recall, the mechanism I proposed was A plus B gave rise to W. And then W reacted with another A to give rise to C. So step 1, step 2. Both steps 1 and 2 are bimolecular steps, meaning that in both steps 1 and 2, 2 reagent particles, right, or in other words, there are 2 particles on the left-hand side of each of these steps. We mentioned molecularities of 1, 2, and 3 are allowed. As far as you're concerned, no step can occur with a molecularity greater than 3. That is a slight bit of a crock, but it is true that they are very, very rare because the probability of the occurrences tends to drop exponentially with the number of interacting particles. So if I were to populate the minima in this reaction, what would I have? Well, certainly 2A and B is the first minimum, that's my reagent. C is my last minimum, that's the product. And I have have here the species present at this point. So what are they? Well, 1A and 1B reacted, which means there's 1A left over, right? Well, when the A and B reacted, they gave rise to W, so the W is present at this point. So again, if I read from the equation, I would say, well, clearly, 1A and 1B gave rise to W, and then the A and the W in the second step reacted to give C. Step 1 is the RDS because it has a larger activation energy barrier. This is the barrier for step 1. This is the barrier for step 2. And therefore, since step 1 has the larger activation energy barrier, step 1 is a slower step. Okay, well, let's imagine then I give you another question. Let's say, make it a little bit more complicated. And let's say we're going to do, let's make it 3A plus 2B gave rise to, let's say, C plus D maybe. And let's make this reaction exothermic, doesn't really matter. We're going to run the method of initial rates, and we're going to do it very badly this time, in that we're going to go ahead and change more than one variable at the same time. And this is never the way you're going to run a reaction, but we're going to do it this way just to make sure we understand what we're doing and how we would go about getting a rate equation from the data table. So I'll have relative rate here. Now remember, what we want to get is an equation that says rate is equal to K times concentration of A to the little a, concentration of B to the little b. I want, in other words, the rate equation. So let's say the data I gave you were, let's say, 0.5, I guess 1.0, 1. Let's say 0.25 maybe. 0.5 and 0.125. Then 1.0, 0.25, in which case this will be 0, yeah, interesting, 0.125 again. We're going to have X, we're going to have Y, we're going to have you fill in the blank, and then let's do blank, blank, blank. Okay? Now, you notice this is a silly experiment because I've never kept the conc of A constant, nor have I kept the conc of B constant. So I've varied them both simultaneously, which is a bad experiment to run. Nonetheless, let's see what we do with it. Well, let's see. So I'm going to ask, what have I done to the concentration of A? And the answer is, I've multiplied it by a factor of 1/2. And we always want to answer the question by what have we multiplied the concentration of A by? By multiplied by 1, by 2, by 1/2, by 1/10, or whatever. Well, if I multiply the concentration of A by a factor of 1/2, it means then that I must have multiplied the rate by a factor of 1/2 to the power of A. Whatever I do to the concentration of a given reagent, I do to the rate of the reaction raised to the order of the reaction with respect to that reagent. Okay? But simultaneously, I actually multiplied the concentration of B also by 1/2. Therefore, I must have also multiplied the rate by a factor of 1/2 to the power of B. So I can then say that what this means is that 1/2 to the power of A plus B, right, because these are both roots 1/2, must be equal to, now 0.125 is really 1/8, right? That's 1/8. But 1/8 is 1 over 2 cubed. So I can infer then that A plus B must be equal to 3. Now, I've got a couple options. This will work if A is 3 and B is 0. And that's a possibility because 3 is the highest order of the reaction that is allowed. 3 is the coefficient of A in the stoichiometric equation. That is the maximal order of A that is allowed. I'm allowed orders of B equal to 0, 1, 2. So this is a perfectly reasonable option. A could also be equal to 2, and therefore B can be equal to 1, and that's allowed. A can be equal to 1, and B can be equal to 2. But I cannot have an option where A is equal to 0 and B is equal to 3. I can't because the coefficient of B in the equation is 2. 2 represents the upper limit of the order of the reaction. So these are my three options for the orders of A, B, and C. I'm sorry, for the orders of A and B. Well, what about the comparison of the first and second lines, first and third lines? And maybe I'll use a thicker pen this time. Let's use that one, red one. So what have I done in going from 0.5 to 1? And the answer is, this time I multiplied it by 2. That means the reaction rate is going to be multiplied by a factor of 2 to the power of A. At the same time, I multiplied the concentration of B by a factor of a quarter. Therefore, the reaction rate must be multiplied by a factor of a quarter to the power of B. So I now know that 2 to the A times a quarter to the B must be equal to 1/8. And I have three options to try on. Let's see. Well, if A was 3 and B was 0, then that would say 2 to the 3 times B times a quarter to the 0, which of course would be 1, is equal to 1/8. And that's not true at all, because 2 to the 3 is equal to 8. 8 times 1 is not equal to 1/8. Therefore, this is incorrect. Well, let's try the other one. What if A were 2 and B was 1? Well, that would mean 2 squared times a quarter, because if B is 1, then a quarter to the 1 is a quarter. So that would say 2 squared times a quarter would be equal to 1/8. Is that true? Well, 2 squared is 4. 4 times a quarter is equal to 1, so that's not true, which means this line is not correct. Now, what it means is, by default, the third line is correct, but let's verify it. That would say that 2 to the 1 times a quarter squared would be equal to 1/8. Is that true? Well, 2 to the 1 is 2. A quarter squared is 1/16. 2 times 1/16 is 1/8. That is true. And therefore, I can report then that the order of the reaction with respect to A is 1. In other words, the reaction is first order in A. And the order of the reaction with respect to B is 2. In other words, the reaction is second order in B. So that I can now write my rate equation as rate is equal to K times the concentration of A times the concentration of B squared. That is the order, that's the rate equation for my reaction. So the reaction is first order in A, so there's an exponent of 1 understood. It is second order in B, where's my cursor? Yeah, second order in B, and has an order of 3 overall. Which of course I figured out from the very first, I figured out the overall order from the very first comparison. Okay, well, let's complete the data table. So I'm going to ask, what have I multiplied 0.5 by to get x? What do I multiply 0.5 by to get x? And the answer is, I multiplied it by 2x. Let's use this one. The answer is, I multiplied 0.5 by 2x to get x. Right? So, if that's true, you know what, I'm going to erase some of these things because it's going to get a little bit confusing. So this is how we get the order, right? I'm going to take some of these things off so that I will not be confusing anybody. And let's get rid of these. Here we go. So we can do this with more easily. And let's get rid of those. And we get rid of you. Okay, let's go back. This one. So what have I done to 0.5 to get x? And the answer is I multiplied 0.5 by 2x. Therefore, the reaction rate must have changed by a factor of 2x to the power of little a, which in this case is 1. Okay, in a similar fashion, what have I multiplied the concentration of B by? Curious. That's weird. What have I multiplied the concentration of B by? Let's write What do I multiply concentration of B by to get Y? And the answer is, I've multiplied 1 by Y. Therefore, the order, the reaction rate should change by a factor of Y to the power of 2. So the number that goes here is 2x, right, times y squared, which is simply 2xy squared. Then you're asked to put in any data, any numbers here that you want, and you can use any set of numbers, but you can't repeat a line. So, for example, I would say, since I don't want to mess with squaring anybody, let's put 1. Okay, I can just put 1, right? Then I can go from 0.5, I can double 0.5 and make that 1.0, and therefore the reaction rate would end up going from 0.5, since I doubled 0.5 to make 1, then the reaction rate would be doubled. I'm not changing the concentration of B, and therefore the overall reaction, the relative rate will be 2. Okay? So I can fill in the data given the rate equation. So once I have the rate equation, I can get the data, I can put in data for the table. Alright, so the next question probably asks you, write a reasonable mechanism for the reaction. So, in fact, what I'd probably ask you is this reaction synchronous? So a reaction that is synchronous, or concerted, these are all the same meaning, or single-stepped, right? These are reactions that obviously occur in one step. So if the reaction is synchronous or concerted or single-step, it means it's a uni-step reactions, right? They occur in one step. Well, the answer to this question is no. And I know that because if it were one step, the molecularity would have to be 5. Because for this to go in one step, 3 A's and 2 B's would all have to react in the single step. It have to all be involved in one step. That's impossible because my molecularity can either be 1, 2, or 3. It cannot be more than 3. So this reaction cannot be synchronous. So I know it has at least 2 steps. So let's do a mechanism given the fact that my reaction is first order in A and second order in B. So I could say, for example, that A plus 2 B's react to give Q in step 1. And I can make that the RDS, make life simple. Then I can say that Q reacts with, let's say, I can make life really easy and say Q reacts with 2 A's, and that will give rise to C plus D. And that's a perfectly legitimate, straight to the point mechanism. So I cross out the QQ's and I get 3 A's plus 2 B's give C plus D, and that's perfectly fine. I could have said that maybe 2 B's react to give, let's say, M, and then M reacts with an A in the RDS to give Z. Well, I have to put the Z as the N. But A reacts with, M reacts with A to give N, and this will be my RDS. Then N reacts with another A, maybe to give D plus O, and then O reacts with an A to give rise to C. It's a bit more complicated, but if I add the steps together, the M goes out, the N goes out, the O goes out, and I end up with 3 A's plus 2B gives C plus D, which is my stoichiometry, right? So both of these, it's 3A plus 2B give rise to C plus D. That's true for both of these. So you notice that in this mechanism, I'm saying that up to and including the RDS, 1A, 1A and 2 B's are involved in the reaction up to and including the RDS. That's also true here, 1A and 2 B's. You notice that I also make D one of my products before I make the other one. Now you want to be careful here because it is okay to create one product before the other. I don't have to make C and D in the same step as I did here. But the one thing you must be very careful of is that you cannot make a product unless both reagents are involved. So I could not, for example, have said 2B react to give D plus W. Because if 2B gives rise to D, then this cannot be right. This equation can't be right, because this equation suggests that for D to form, both 2B and, well, both B and A must be involved. So it doesn't have to be both 2B's and all 3A's have to be involved for a C or a D to form. But the point is that neither C nor D can appear unless A and B, however many of them, have entered the fray. Right? So I could not have written this mechanism, 2B gives rise to D, and then W reacts with, say, 3A's to give C. This mechanism is wrong on many fronts. One, we are making a product without the appearance of both reagents. Wrong. Two, the second step has a molecularity of 4. Wrong. And then whichever step I pick here as the RDS wouldn't be right, because if I pick this one, the reaction should have been second order in B and 0 order overall, 0 order in A. So second order in B and 0 order in A. If I pick this as my RDS, then the reaction will be second order in B and third order in A. So this mechanism is wrong on many fronts, and you'll be getting questions like those that say, critique a given mechanism. So let's say, and of course we have no other way of determining which of these two mechanisms is correct, right? Even though we're never really looking for a correct mechanism per se. Because both of these are consistent with both the kinetic data and the stoichiometric data. So both of these are reasonable. If I asked you to, for example, draw the reaction profile diagram for this one, what would it look like? Well, again, I'll have my reaction profile diagram. I'll have H against reaction coordinate. And did I say this was exothermic or endothermic? Cool. Exothermic, very nice. And we are saying that in this mechanism, so I'm saying that we have just exothermic. I'll give myself room because we actually identified 1, 2, 3, 4 steps. Give myself some room. Here I'm going to have 3A, 2B, those are my reagents. Here I have C plus D as my product. So step 1 gives rise to some species. Then there's an RDS, step 3, and step 4. So what species do I have at the minima? Well, in the first step, both 2B's are gone, replaced by M. The 3A's are still there. The M and one of the A's succumb to give rise to N. So that leaves behind 2 more of the A's. The N and one of the A's react to give D plus O, which means the other A is still left. And then the last step, the O and the A react to give C. The D simply persists. And that would be the reaction profile diagram for the second mechanism. And again, as I pointed out before, you really want to make sure that if you mean for the second step to be the RDS, then you draw it quite emphatically that that step has the highest acquisition energy barrier. Okay, so we can do this question from a different angle, which is the following. Let's say I give you a reaction profile diagram instead, which is kind of a straight line in this thing. So I've got H against reaction coordinate. And let's say I have this as my, so I go, oops, heck of a gradient. Let's say I go here, to here, to here, to here. And I say A plus 3B, then let's make this make this m, let's make this 2a, shall we? 2a plus b. So I have m plus a plus b. Then here I have, let's see, again, c plus b again. Let's make it 2c plus d. Then here I'm going to say I have 2c plus b plus q. Okay, good. So I think that's going to work. Okay, perfect. So here's question 1. Write the overall equation for this reaction. The overall equation is going to be, and so all of this crap in the middle is irrelevant. The equation is the conversion of the reagents 2a plus 3b into the products 2c plus d. So my equation is simply 2a plus 3b gives rise to 2c plus d, and I will indicate that the reaction is an endotherm. Okay, that's question 1. Question 2. Write the mechanism for this reaction. Now, it would not be necessary to say identify the radiative step, because that's what part of the mechanism is. You misidentify the RDS. Similarly, if I said to write the equation for the reaction, I wouldn't just write 2a plus 3b gives 2c plus d. I'd indicate if it's exothermic or endothermic, right? So the question doesn't have to tell me to do that. I would do that by my own accord. So what's the mechanism? Well, it's certainly a 3-step mechanism. So I'm going to write 1, 2, 3. Right? Because I've got 3 humps. 1, 2, 3. And I already know that of the 3 steps, step 1 is the RDS. So whatever step I put here, I'm going to put RDS for step 1. Right? Because that is the one with the largest artificial energy barrier. Now, it's not the one with the highest transition state energy, but that's irrelevant. The rate determining step is the one with the highest gap between the preceding minimum and the transition state. The preceding minimum and the transition state. Okay? So even though the transition state here is the highest, the gap between it and the preceding minimum is actually only the second highest in the system. It is therefore not the one that dictates the rate of the reaction. So what has happened? Well, I have 2 A's and 3 B's. At the end of step 1, I have 1A, which means one of the A's reacted. I have 3 B's at the beginning of step 1, but at the end, I only have 1 B, which means that 2 B's reacted. So those are the reagents of step 1. In other words, step 1 has a molecularity of 3. It's a termolecular step. What did I make? Well, I didn't make A and B because they were present at the beginning. What I made that is new is an intermediate M. Okay. Now, M is present at the start of step 2. It is not present at the end. So step 2 must have involved M as a reagent. There was an A present at the start of step 2. It's gone at the end of step 2. So A must have reacted. Right? The B, which was present here, is also present here, which means it didn't participate in the reaction. I'm not going to write it as a participant. What did M plus A give? Well, who is new? There are 2 C's and there's Q. So I made 2C plus Q. Fine. What happened in the third step? Well, there's 2 C's here, but they're also in the product, so 2C did not react. So I made one of my products, well technically 2 of my products, and that's okay as long as they are formed after both A and B are involved in the reaction. Well, B was here, as was Q. They are no longer in the product, so B plus Q must have reacted, and they gave rise to D. And of course, obviously when I sum these together, the M goes out, the Q goes out, and I have 2 A's plus 3 B's give rise to 2C plus B. Okay? The next question might be, what are the molecularities of the step? Well, as we said, step 1 is termolecular, step 2 is bimolecular, step 3 has a molecularity of 2, in other words, it's bimolecular. write the rate equation for the reaction. So the rate equation is going to be rate is equal to K times the concentration of A to the power of 1, because there's only one A that's involved, up to and including the RDS, times the concentration of B all squared. That's my rate equation. Now, I say this every year, and every year people, just make the same mistake. The rate equation is an equation. It must have something is equal to something else. The rate equation is not K conc A conc B squared. It is rate is equal to K times conc A conc B squared. The rate equation also is not rate is equal to conc A times conc of B squared. There's a rate constant that needs to be featured in the rate equation. Alright, next thing would be to draw a data table with, let's say, 3 lines of entry that would be consistent with the observed kinetics. So construct a table that's consistent with the observed kinetics. So I'm using the method initial rates. So I've got conc of A subscript 0, conc of B, subscript 0, and then relative rate. Now, I'm not going to make my life hard. I'm going to pick 1, 1, 1. Those are easy numbers. I'm going to double 1 and keep the other one constant. In other words, although I may give you guys a question that is tricky in the sense that I'm varying 2 things at the same time, I'm not going to give you bonus points for making your life hard, right? There's no value to that. That's my job. So I'm going to vary 1 thing at a time. So I will double conc of A and keep conc of B constant. Now I know if I double conc of A, if I multiply conc of B by 2, I must multiply the rate by a factor of 2 to the power of 1, which is 2. So the number that goes here is 2. I'm going to go back to unit concentration of A, and now let's say I double conc of B. Well, if I multiply the conc of B by 2, I will multiply the rate by a factor of 2 squared, which is 4. So the number that goes here will be 4. And that's a table that has 3 lines of entry, 1, 2, 3, that is consistent with the observed kinetics. So you can be given this question either what I call forwards, where you're given the table, right? Where you're given the table, and you're asked to find the order of reaction with respect to each reagent, and then the overall order of the reaction. Then to construct a mechanism, come with a mechanism that's consistent with the data, and then to draw a reaction profile diagram. Or we can go backwards, which is, given a reaction profile diagram, I'll ask you to give me the overall stoichiometric equation, including the sign of delta H. Draw the mechanism. Of course, here you have no freedom, right? You can't invent the mechanism, because the mechanism is given to you by the reaction profile diagram, right? So I can't make up a mechanism. It's given to me. It's defined by the reaction profile diagram. And then you're asked to write the rate equation. That's also defined by the reaction profile diagram. And then to construct a data table. And usually you have 3 or 4 lines of entry. And it has to be obedient to the rate equation. The only caveat is don't play Superman or Superwoman and try to make the numbers complicated. You get no bonus points for making this 0.0178 and this one 0.3573, right? I mean, you get no bonus points for that whatsoever, right? Don't make it complicated. The only other point I'll make is that if I have a reaction, just to make a point that's it's a little bit subtle, if I have a reaction that is 0 order in a certain reagent, let's say for example I had 2A plus B gave rise to C. And it turns out my rate equation from the kinetic data was rate is equal to, let's say, K times conc of B only. So the reaction is 0 order in A. Well, what that means, let's make sure we understand something here, is that if I have, say, conc of A, conc of B, subscript 0, I mean, of course, this is my relative rate, okay? If I have, let's say, 1, 1, 1, and let's say 2, 1, I'll put nothing here for now, and then 1, 2, and then let's just for the heck make it 2, 2. And I want these things. I'm actually running the experiment, right? Well, if the reaction is 0 order in A, then doubling the conc of A would cause the rate to be multiplied by a factor of 2 to the 0, right? Which of course is 1. So in other words, I'll have no change in reaction rate. So doubling the concentration of a reagent that the reaction has a 0 dependence on, right, in terms of the kinetics, will not change my rate. So if I multiply conc of A by 1,000,000, the rate is unchanged if I kept conc of B constant. Here, if I double conc of B, regardless of the concentration of A, the reaction rate will double because of the linear dependence of the reaction on B. Similarly here, if I double conc of B and I double conc of A, the reaction rate doubles because I double the conc of B. Concentration of A is irrelevant, so I'm going to have 2. So this is consistent with a reaction that is 0 order in A and first order in B. Now, what would happen if I made this number 0 and I made this number 100? What happens to my reaction rate? And the answer is, the reaction rate drops to 0. And that seems kind of odd because, hey, the reaction rate does not depend upon the concentration of A. So if I multiply conc of A by 0, nothing should have happened to the rate. That's what we would think. But that's not true. Because what the reaction is telling me, what this tells me is both A and B are required for C to form, right? B does not give C by itself. B requires A for the reaction to go. So all this rate equation tells me, all this tells me is who is involved in the reaction up to and including the RDS. So it may have been that B reacts to give M, right? And then M reacts with 2A to give C. So by itself, B in the RDS will give rise to M. But unless the A's are present to react with the M, I get no product. So although the reaction rate is independent of the concentration of A, the reaction itself is not independent of A. Because in the absence of A, there is no reaction. Okay? So if the concentration of one of the reagents in the equation drops to 0, the reaction simply does not go. And I get a rate of 0. Okay, so we'll stop here and we'll pick up, this is 40 minutes, we will pick up one more lecture. Now, if you guys look at this before Friday afternoon, that would be great, but Blackboard will be down until sometime on Saturday. And my expectation is you guys will look at this maybe Saturday evening or Sunday. Look at the second lecture Saturday evening or Sunday, because I'm going to expect you guys to have seen them both by Monday's lecture. Okie dokie. I'll see you guys in the second lecture.